X is not defined, then define it. All of this code down here will then be spit out as part of the output of the preprocessor. The end if here matches this if end if. So everything in between these is only conditionally included if this symbol is not defined. What that does is it helps protect us if we're doing multiple includes and we have this recursive inclusion chain. The one where A includes B, B includes C, and C includes A again, for example. Then if we have this chain that's going to go on, the preprocessor with just left to its devices would eventually run out of memory by recursing through all of those and include and include and include. So by using the if end if, we basically say if this file hasn't been included yet, then remind the preprocessor that it's been included and include it. So these contents would only show up the first time this file is included in a particular compile. So it's protecting ourselves against possible loops in the inclusion. Not everybody does it this way, but I do this ritually on my header files. And I take this symbol here and I name it after the file so that I don't have multiple files with the same symbol. Because if I have more than one file with the same symbol, then I have the reverse problem. I wouldn't be including everything I wanted to include. If everybody used X, for example, only the first include file would be included. Yeah, okay.
All right, the copy constructor we talked about on Wednesday.
Okay. So,
moving on from the first question I had.
yes, so I have a copy constructor. Something like that?
Yeah. Well, I was studying online examples, and they have that a lot, except the and right after the name of the.
This here?
Yeah.
Some of them don't have this, some of them do.
Or they'll put it right after the name of this class. What is that?
Okay, so it'll either go here, or there'll be a space and put it in the middle, another space, or they can put it over here.
And does that all mean?
None of that matters.
Okay.
The ampersand means that we're passing it by reference. Over here are some code that executes this. I have an object of type X named A, and then an object of type X named B, which is being constructed as a copy of A. So this invokes the copy constructor. This does not. Okay, when the copy constructor gets invoked at this point, A is the parameter that gets passed in. And the ampersand means don't copy A's values, actually let this code access the memory where A is stored.
Okay.
And so whenever we're in this code and we refer to SRC, we're actually referring to the actual memory where A is stored. That, for efficiency reasons, if class X has a lot of memory associated with it, that's more efficient than copying it to send it in. We're actually sending it, we're able to access it directly and not have to copy it, just to copy it again. The other issue is, if we actually wanted to copy it to send it in, that actually invokes the copy constructor.
Right.
So it's got to be passed by reference.
That's, yeah, I noticed that as one of the examples of an infinite loop.
Yeah. So we call that pass by reference. It just means that even though SRC is not a pointer down here, we use it like we do a normal object with using dot to access its data members instead of the arrow. It's really referencing the same location in memory.
And then on the homework, we were supposed to have the social security number be a static array?
I regret the wording in the question, in the homework to begin with.
We're not using the static keyword.
Don't use the static
Okay.
keyword. What I mean is an array of a fixed size.
Cool, I'm done.
Okay. Is that your laundry list?
Yep. Oh, I have the deep on the assignment operator. I think it's the same kind of thing. It's different than the other comparison operator.
Yeah. So the assignment operator's signature. Let's see if I'm actually in the implementation here, as opposed to the header file, right? Operator X no offense. Oop. Need an equal sign there. Assignment operator, right?
Yes.
Okay, this is actually identical to this.
Okay.
My code, I choose source here, I choose RHS here, but that's just me. What this is doing here is allowing us to do that, correct?
Yes.
Okay, where in this case, A gets passed in there by reference. Meanwhile, B is used up in this code by using the this pointer for accessing B. The return type here means that our return statement is almost always like that. We're returning a reference to B when we return, which allows us to have code that looks like this. And so we can do assignment chaining. A's value can be copied to B, and then B's value can be copied to C. And that actually is a legal C or C++ statement.
Okay.
So that's what this return value is for. And we pass it by reference rather than a copy of it, because that's a lot more efficient than passing back a copy.
Okay. So the and is part of the...
It's part of the return type.
Alright, that's my list.
Cool. Other questions that have been coming up that we maybe put in somebody else's list?
Well, I'm pretty sure I did that without doing the reference.
On your return type for your assignment operator?
Yeah.
Okay, let me tell you then what's going to happen when you actually use your assignment operator. Your assignment operator will receive the right-hand side by reference. It will copy everything, and then it returns this. Since there's no reference there, then on the stack, we actually, the compiler generates a temporary object of type X using the copy constructor, copies the entire contents of this onto the stack, and then that gets put in place for the next assignment if it's necessary. And if there is no other assignment, then it gets thrown away after that. But your copy constructor will be used to make an identical copy of the object you're returning. So if your object is of any appreciable size, then you're going to have a major inefficiency.
Better double check that.
When it comes to the operator overloading and copy constructors and so forth, I just kind of have my almost set of commandments that I follow as far as this is how I do them. And if I follow them correctly, then I'm following best practices, even though there might be other ways I can pull it off. But those are my best practices. And that's what I'm trying to present to you when if I say this is the way to do it. Sometimes there are other ways, but they're usually not as good. Okay, if I look at the schedule, not this week, but next week on Wednesday, we have a midterm exam. Everybody's excited about that.
Always, of course.
Unfortunately, that also means that next week I won't give you the opportunity to have an assignment.
What?
I can throw up some sample problems you can play with just for fun. We do have the semester break next weekend as well, so Thursday and Friday of next week there won't be any classes. That doesn't affect our schedule here, but that's also in the mix there. So this week you're supposed to implement a linked list. Now I've asked this question before, I keep forgetting. People that are in or have completed 2420, the data structure class?
Yeah, we're in it.
Everybody's in it or has completed? Okay, you've talked about linked lists in that class.
Linked lists?
Linked lists.
Explain a little bit, and then I'll tell you.
Well, he said we could,
That's a no.
yeah, he said we could implement our stat class with a Python list or a linked list, so it's been mentioned, but that's about it.
Yeah,
What's the assignment word?
Well, cool. Maybe we'll make things a little bit easier for you in your data structure class by covering this material now, and you can cover it again in there.
Okay.
Okay. Your assignment this week is to implement a linked list to store your student class. And so we'll look at what that means here. So a linked list, basically, let's say that I'm not going to use the student as my example because then I'll just be completely doing your assignment for you. But we have a concept of a node when we talk about a list. A node is a collection of data. This is the data right here. Packed together with a pointer we call next. If I have multiple nodes collected together, remember each one of them has a data section and a next section, then I can link them together because next is just a pointer to the next object in my list. Okay, so if I had a list with 3 items in it, it might look like that. And let's say for now that I'm going to be very boring, I'm storing letters, characters in my list. And so I've stored the characters A, B, and C in my linked list here. Okay. So basic structure, nodes that have data and next pieces to them. Some finer details. A has a valid next pointer, right? B has a valid next pointer. C is the end of the list. So it doesn't have a valid next pointer, and yet it's still a node, so it has to have the next pointer. How do we clean this up to make sure that we can understand when we've reached the end of the list?
Link to A?
Link to null.
Okay, both great suggestions. Link to A makes us have a circular list, and we never know when we reach the end.
Okay.
Which is sometimes desirable, not in the case that we're looking at in the simplest case. A pointer to null, or a null pointer, if we put a null pointer in there, then that means when we see a null pointer for next, we stop. We can always know that. The null will never be a valid pointer. So if we put the special value 0 in the next pointer, then we know that we're done. Okay, the last detail here. When we talk about a linked list, we have to know where we start from, and we usually call that the head of the list. So this is a typical representation of a 3-element linked list. We've got the head, which is basically only a pointer to a node, and then nodes, which have data and pointers to nodes as we go. Let's talk briefly about what the node class might look like. And right now, I'm not too terribly worried about what the methods are. I'm more concerned about are the data members given the pictorial representation? What are their names?
Head for data members.
The data members of the node class.
Oh, okay.
Data and next.
Data and next. Okay, the type of the data member depends on what type of data we're storing, right? The example I've drawn on the board, it would be a char. We're going to write this a little bit more generically. I'm just going to say data type. To me, if you're storing a student, for example, you'd say student S or student data or whatever you want to call it. If I was storing a track, I would say track data. Whatever type you're storing in your node, you would put here, right? Okay, and what type is next?
Would it be an int
So
or an index?
it actually points to another location in memory. All of these nodes, all three nodes that I have here, have been allocated dynamically off of the heap. So they're somewhere out there in memory. Who knows exactly where?
So it's a pointer.
So it's a pointer. And what type does it point to?
Well, it's pointing to data. It's pointing to data type, right?
Actually, this arrow means that it's actually pointing to the entire node,
Okay.
which is comprised of a data and the next piece. But it actually is pointing to the entire node.
Okay.
So, our node class has two data members, the data index, next being a pointer to a node. That seems recursive in a way, right? The node class has a pointer to another node object. It's okay that way. In fact, it has to be okay that way. Okay, meanwhile, when I'm tracking and representing the head of this list, I would then have an additional node pointer that's external from the node class to represent the head. Okay, so let's assume that I've got some code up here that code that I'm not filling in has constructed this particular list. Okay, so now I have a list. Head points to a node, that points to a node, that points to a node that has a null pointer at the end, right? So it's all been constructed. Now I want to display the data from each of those nodes in order, starting with the first one and going to the last one. I just want to display it to the screen.
So you're wanting us to tell you the code?
So what do you think I need to do? What's
Probably a for loop.
some sort of a for loop, right? Okay. All right, some sort of for loop.
So for
Node I.
You're saying node I like that?
Well, I was saying count with a node type. I guess that won't work.
so you'd
So
want
we don't actually have an array, so we can't use indexing here. Right?
we don't.
This is not an array. This node is not contiguous in memory with this node or this node. They're not necessarily anywhere related to each other as far as memory goes. They're somewhere on the heap, each one of them individually allocated, not necessarily sequentially stored on the heap. So let's backtrack for just a second. Let's write some scratch code over here. How can I print the data of the first node given that I have the head pointer.
A dot data.
Okay, if there was a variable called A, the only variable I have is head.
So it'd be head, pointer, this? Or no?
No.
Head A dot, or head arrow data.
Okay, head is a pointer to a node. This node here. And that node has a data member called data.
And it only points to data.
No, head, from head I can access either the data or the next data member. I can access either one of them. The important thing is that head is pointing to that, it has the address of that object. So once I have the address of an object, I can get at its members by using the arrow operator. Okay, I'm actually violating this public-private thing.
So you don't want private anymore?
We're going to throw that out for now because it just complicates our issues. For now, we'll get rid of it.
We can't do that.
I was gonna say, wouldn't you need like a get data if you were doing it that way?
That's right. If we had to get data, we would say get data here instead. That's right. So that's the way we should do it, but I was being lazy. Should I not be lazy?
I already scribbled it out.
All right, I'm going to be lazy for now. Okay? Sorry. Thank you. There's some other.
So the head object is of the node class, right?
It's a pointer to the node class.
So it has, would it have a next data member also, or a next member also?
It would. I can talk about its next like this.
So which do we want?
Okay, well, if I were just going to display the contents there, I would do something like standard, cout, arrow, arrow, head, arrow, data, and my indel. That would, assuming there is an output operator that knows how to display data type, that would then display the data that A points to. The data part of that node.
So are you able to do like a for I not equal null? And then,
So
I mean, because the
wanna
only
keep-
time we'd stop is when there's a null.
As long as next is not equal to null, we want to keep going, right?
Right. So do we want a while loop? Would that be better?
Oh, we can do it either way. So I'm going to do it like this. I'm going to declare a loop variable. Rather than calling it I, I'm calling it cur. That's short for current. The current node, the node I'm currently looking at. It's a node pointer, right? So my for loop starts off and says, cur needs a point at the first node.
Okay. And then,
As long as cur is not equal to null, the null pointer, cur should become cur next.
it just doesn't seem like that should work.
So
I mean, just if you're using next as every,
let's trace it as a loop, okay? So cur, we initialize it and it has a random value in here, or we create it and it has a random value in here, right?
yeah.
Then the first, remember our way a for loop works. this initialization happens once, this test happens before each body is executed, and this happens after each body is executed. So we initialize it by copying this pointer down to here, which means cur points there, right? Then we say just if cur is not equal to 0, it's not equal to 0, right? So we execute the body of the loop, and then what do we do here? Remember when we have an assignment operation, the right-hand side of the operation, that expression is calculated first. Its result then is copied and assigned into the variable on the left-hand side of the assignment.
Okay.
So the right-hand side says cur next. It goes and finds this pointer right here. And then what does it do with it?
Stores it as current.
It assigns it into cur, which means cur now points there.
And it checks if it's 0.
Checks to see if it's 0 because we're at the top of the loop again. It's not 0, so we execute the body of the loop, and then we go to cur next and copy that pointer back here, erasing the other pointer, right?
Okay.
Cur is not equal to 0, so we execute the body of the loop. The bottom of the loop. We go to cur next, and we copy that pointer back over here. And we say, is cur not equal to 0? That's false now, so we don't execute the body of the loop, and we terminate the loop.
So, for accessing the data member, we can't just say head arrow data, because then it wouldn't be head the next time around, would it?
Right, right. We'd end up printing out the A 3 times if we did that, right?
Yeah.
However,
So if we say node arrow data, because head's never going to have data, or will it?
no, head arrow data will always point to this.
Okay.
And so we'd end up printing the A 3 times if we had head arrow data. However, each time we're inside the body of the loop, the consistent thing about the body of the loop is cur points to one of these in succession. So if we ask cur data, then since the pointer cur changes each time, we're pointing to a different set of data each time. And so we can display that data in sequence. Maybe it's okay?
I get it now. Yeah.
What questions do you have? So, for me, the first time I really felt like I got it, I thought, wow, how beautiful is that? Because it's a loop. It has all of the elements of a loop, it's just not contiguous memory, so we're not using an integer to loop through, but it's got this built-in terminator for itself. It's got an easy increment statement once you understand what the increment statement is doing, because it's just walking down the list. It has a very defined initialization statement, so it's a nice, beautiful loop. And down in here, the loop, what do we call those, invariant element is a cur points to one of the elements of the list.
So I guess my question would be how to initialize the node. Do you have it a null character at next as default, like when it's initialized, and
So-
then you overwrite that if there's another element added, or?
Right, right. So your constructor for your node class would put next equal to the null pointer, because you don't want it pointing to random memory. That would be the safe thing to do.
I guess we get there or something.
And we need an assignment operator too, right?
Actually, you're pretty lucky in this case in that you don't need an assignment operator for the node class, because when we deal with the node class, we're only dealing with the pointer to a node class. We're never actually copying nodes around. we're copying their pointers around. We just have to be careful that we don't juggle incorrectly and drop a pointer somewhere. Or use a pointer twice. Because if we use a pointer twice, we could end up with a circular list here, right? And then this for loop would go on forever.
So since her and head are both the type pointer, they already have an assignment.
Yeah, the assignment for a pointer is basically a big integer. And so then there's a built-in operator that already does the copying of a pointer data. So there's no, it's not tricky like it was with the assignment operator on our student class where we had internal pieces of information that were being duplicated.
Okay.
Cool, these are good questions. Any more? Okay, all we've looked at is if we have this code that I hid from you that actually has a list in it, how do we loop over it? Now, let's look at making changes to our list. Okay? Is it okay if I end up erasing this? You got it recorded if you wanted it. By the way, this has a name. We call it traversal. Whenever we have a data structure, some collection of data, we talk about how do we traverse the data and look at all of it. This is the traversal for a singly linked list, which we refer to as linked. Okay, so after we have a little bit of chalk talk over here, I'm going to go and erase that board and write some more code. Let's add. Let's insert another item into this list. Now, if we insert an item, we have multiple choices for where to insert it. We could put it at the front, in front of the A. We could put it at the end, after the C. We could insert it anywhere in the middle, in between B and C, or in between A and B, right? Okay. We're going to just choose a single convention with our list that we're going to construct here in class, which will be the same convention that's okay to use on your assignment. And that convention is, I don't really care if the contents are ordered here. A, B, and C, just I wrote them down randomly, and they happen to come out in order. That's not what we're after. We're not after a sorted list, okay? It's okay if they're in random order. Because of that, we are going to only insert at the front of the list. New items will only go here at the front. We could put them all at the end, but that means we'd have to traverse the list to find the end to put it on the end. And we're not going to do that. Okay? We're just only going to stick it on the front. So let's assume that I allocate a new chunk of memory for a node. I stuff my data value in there, and now I want this to go at the front of that list.
So next equals the address of A.
Okay, so this node's next needs to point there, right?
Yeah.
Head needs to point to D.
And head needs to now point to D. If we do that, then, ignoring that black line and using these green lines, we now have a linked list, right? With all 4 items in it. Okay. So step number 1, I allocated the node itself, right? Step number 2, I inserted the data. Step number 3, I set the pointer, I set it next correctly, and finally, step number 4, I updated head, right?
And it doesn't matter if you switch those around too much though, does it? I mean, you need to have the allocating memory and then the inserting data.
So this must come first, right? If we haven't allocated the memory, we can't assign it to its data members. Number 3 has to come before number 4.
Okay, that's
Otherwise, if I first say number 4 goes there, points down to here,
You've lost.
3 actually gets, this next actually gets initialized from the value of head. And I will have lost head's previous value if I overwrite it. So I must first make this next point and then make head point. So 2 and 3 can be reversed, but that's the only reversal that's legal that I can see in the ordering.
So when you're inserting a point, do you take the address of it then from, say, head or the previous next and store it? I mean, like, so you would
When we
assign
do
next,
this?
yeah,
Okay, let's go ahead and do it.
okay,
Is that all right?
yeah.
Okay, remember, all this mysterious code up here is already run, so we have the 3 element list here already to go. So my first step is allocate a new node, right?
Mm-hmm.
And I'm going to store that in a temporary variable here called T, because I'm not going to write a lot. Okay? So that's step number 1. I've allocated space. Okay? Next step. Step 2. Whatever it takes to initialize my data, right? These are not comments, those are number 1, number 2. Not. There we go, is that?
So they are common.
Now they're comments. Okay. Alright, so step 3. I need to set up next. What do I set it equal to?
Well, in this case, you'd set it to
Remember, head is a pointer, and so is T. T sitting down here, right? T is pointing there. Head is pointing there, but I want T's next to point to that same spot. So I just copy this pointer, which is some address number. I copied over there, right? Okay, finally, number 4, what do?
head is a pointer to T.
Okay, so head is already a pointer, right? And T is already a pointer, so we're just copying the address that T has and putting it into head there. And that is our insert or add node method for adding to the front of a list. And for an unordered list, we might as well add it in the front. It's the most efficient way to do it, as far as the amount of runtime our code needs. Any questions? It's almost trivial when you look at it that way, right? It's just important to make sure you get the ordering right. Otherwise, as we talked about, if you swap those two, then we end up with problems.
One question I have is when we work in Python, adding to a list would always add to the end, and then if we wanted that to be at the beginning, maybe we'd like swap or sort or something. Why is it easier in C to just place it at the front?
Python lists have implementations under the hood that make it easy to access the end or the front of the list.
Okay.
And this is a singly linked list, And with a singly linked list, the only thing under the hood we have is head, which means that only the front is easy to access.
Okay.
In Python, they have doubly linked lists, which have a head pointer, or a prev pointer, I should say, so that each node knows its previous as well as its next neighbor. And there's a tail pointer, which points to the last node in the list. There's different mechanisms to make it easier to walk around with it.
Okay.
And we could do that, but as our first example, I didn't want to.
All right. I was writing something else when you wrote the node pointer t equals a new node. What was the, are we dynamically?
So the new node, this memory right here, is being dynamically allocated off of the heap.
Okay.
Yes,
Okay.
that's what the new node is doing for us. So realize that if we were using stacked memory, we wouldn't be able to even do this, because as soon as a function returned, the memory we were trying to point to and build a list up out of would evaporate, right? And so we'd have all sorts of memory corruption. But with the heap makes this possible.
So what about in our for loop, current becomes a null, right? Because that's a node pointer.
When we hit the end of the list, it becomes null.
So do we need to free up anything there? Do we
Okay.
need to delete current?
So as long as we want this memory, this list to stay in memory, we don't delete it. Head is a pointer to the first element, which points to the next element, which points to the next element. So all of these elements are still active in the list. At the point we no longer want our list, then we have to go through and free up all the existing nodes. But until then, we don't want to delete anything. Remember, cur is a pointer to elements within this list.
Okay.
It's not a copy, it's not new memory, it's just a pointer to memory that's already part of our list.
Okay.
So we don't want to delete within it.
Pointers and non-pointers is still getting this up.
It's one of the really cool things about C and C++. It's also probably the most dangerous part of C and C++, because it takes a while to get it down. So it's okay. Keep working with it. All right. So I feel like I've given you a way to traverse and a way to insert. I haven't given you a way to delete. What if you do want to get rid of something out of your list?
Are you talking permanently or just removing it from the link?
Permanently get rid of it. So I'm going to go back to our 3-element list now. Okay, if I wanted to get rid of this node here,
Well, you'd have to make a temporary variable that holds the address of it.
okay, so let's make a temporary variable t that holds the address of the thing we want to get rid of.
And then you would want to,
Or maybe the thing after doesn't even want
you'd want to, yeah, you'd want to go, you'd have to save B's next to A is next.
Like that.
Yeah. And then you'd have to delete B.
And I'm going to write that right here because I don't want to destroy my wonderful drawing.
And
And
then I think you're good there, right?
now we have a list of length 2, right? And we've eliminated this memory, we've deleted this memory. So we don't have a memory link either. That seem reasonable? got two vocal inputs here, so the rest of you, I assume that you're good unless you're saying something.
What do you need the pointer T for? Is it temporary?
Okay, if we don't have the pointer T, then when it comes time for step number 3, which is to delete this memory, we no longer have its address. And you delete using the address. Good. More questions? Okay. So code for this. Node star T equals, I'm going to write this a little bit weird here. Actually, I don't want it to be called cur. I'll pray out. So we're assuming that we have somehow located A as being the node right before the node we want to get rid of.
So we're basically in a for loop right now. I mean,
So somehow we've used some sort of loop to find this, right? We're not going to have time to go through that particular loop today. We'll get it Wednesday, okay? So if prev points to the previous node, then we take prev's next, which is this address right here, right? And copy it into T. That's step number 1. Then step number 2 says prev's next should become
cur's next.
cur, or in this case we're calling it T.
Right.
T's next, right? Step number 2. T's next holds the address that we want to be over here. Okay, finally,
Delete.
we need to delete T. Notice the absence of the brackets. Why are there no brackets?
It's not technically a list.
It's not an array. T points to a single node, not an array of nodes, right? And the biggest sign for that was when we had our add code over here, we said new node without brackets, right? So we're only allocated the nodes one at a time, so we only delete them one at a time. So there's no brackets. Okay, that's the delete code if we're deleting something out of the middle. I'm sorry we're out of time for today. Delete's not quite as simple as all of that. Delete has 3 possible cases. We're deleting somewhere in the middle, which is what we've looked at. We're deleting the last node in the list, which we need to evaluate, or we're deleting the first node in the list, which we have to evaluate as well. So, for all of that, we'll have to deal with that next time in a little bit more detail. Once we have that down, it'll be easy to wrap it up. Okay?